The Principle of Additive Volume. Welcome, everyone. Today, we are going to begin a new topic titled, The Principle of Additive Volume. Now, before we dive into the new material, let's take a moment to reflect on what we have already mastered. In our previous lessons, we focused on calculating the volume of individual, standard geometric solids, things like cubes, cylinders, cones, and spheres. You should all feel very comfortable with those specific formulas. However, as we move forward, we need to look beyond these simple, isolated shapes. In real-world scenarios, the objects we encounter are rarely just a single, perfect cube or a lone sphere. Instead, they are often complex structures made by combining two or more of these basic solids. To tackle these more complicated shapes, we are going to use a very important concept called the Principle of Additive Volume. Over the next few slides, I will show you exactly how this principle works and how it differs from other measurements like surface area. Understanding the core concept. Now, before we jump straight into the calculations, I want us to pause and focus on a very important distinction. It is crucial to understand a fundamental difference between how we handle surface area and how we handle volume when we are combining different solids. Let's look at the case of surface area first and why we call it non-additive. Imagine you have two separate blocks and you glue them together. When these two solids are joined, the faces that touch each other are no longer part of the exterior or the visible surface of the new, larger object. They are now hidden inside. Because these joining faces essentially disappear from the outside, you cannot simply add the surface areas of the individual parts together to get the total. If you did, you'd be including surfaces that aren't actually on the outside anymore. Keep this distinction in mind, because as we will see in the next slide, volume behaves in a completely different, much simpler way. The case of volume additive. First, let's define what we are actually working with. Remember, volume is simply a measure of the total three-dimensional space that an object occupies. Now, I want you to draw a distinction here between what we discussed in the previous slide regarding surface area and what we are doing now with volume. As I mentioned earlier, when we join two shapes, some of their surface area disappears because those faces are now hidden inside the object. However, volume behaves very differently. The space occupied by a solid does not disappear just because it is joined to another solid. Think of it this way: whether you have two separate wooden blocks sitting on a table or you glue them together to make one single object, the total amount of wood, the total amount of material, remains exactly the same. The space they take up doesn't change just because they are touching. This brings us to our fundamental principle. Because the material doesn't disappear, the total volume of a complex solid formed by joining two or more basic shapes is simply the algebraic sum of the volumes of its individual parts. To put this into a mathematical formula that you can use in your calculations, if we have a complex solid that is composed of solid A and solid B, then the total volume equals the volume of solid A plus the volume of solid B. Now let's move on to slide 3, where we get to the heart of our topic, the case of volume. It is as simple as that. We are just adding the pieces together. In the next slide, we will see how we can apply this exact logic to a real-world object, like a medicine capsule. Real-world example, the medicine capsule. Now that we understand the theory behind why volume is additive, let's put this into practice with a real-world example. Take a look at this image of a medical capsule. If you look closely at its structure, you'll notice it isn't just one single shape. It's actually a combination of different geometric solids. Specifically, a capsule is designed with a central cylinder and two hemispherical ends. To find out exactly how much medicine this capsule can hold, which is essentially finding its total volume, we are going to apply the principle of additive volume that we just discussed. To solve this, I want you to follow a systematic, step-by-step breakdown. In step 1, our goal is to decompose this complex solid into basic, recognizable shapes. By observing the capsule, We can clearly see it is made up of one central cylinder and two hemispheres, one located at each end. In step 2, we can actually simplify our work. Since we know from our previous lessons that two hemispheres with the same radius, let's call it r, fit together to form one complete sphere, we can simplify our components. Instead of calculating two separate hemispheres, we can simply treat the capsule as being composed of one cylinder with a radius r and a height h, and one single sphere with the same radius r. This makes our upcoming calculations much more straightforward. Volume formulas for capsule components. Now that we have successfully decomposed our capsule into its basic geometric components, the cylinder and the sphere, we move on to step 3, which is to state the individual volume formulas for each part. First, let's look at the cylinder. The volume of a cylinder is calculated as pi times the radius squared, multiplied by the height. Next, we need the formula for the sphere. The volume of a sphere is 4/3 times pi times the radius cubed. This brings us to the most important part of our lesson, step 4, where we apply the principle of additive volume that we discussed earlier. Since volume is additive and doesn't change when the shapes are joined, the total volume of the capsule is simply the sum of these two volumes. Mathematically, we express this as total volume equals the volume of the cylinder plus the volume of the sphere. When we substitute our formulas into this equation, we get our final working expression. Total volume equals pi times the radius squared times the height plus 4/3 times pi times the radius cubed. As we move to the next slide, keep in mind that while this formula looks complex, the logic is straightforward. We are just adding the space occupied by each part together. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even when you understand the principle, it is very easy to make small errors that can lead to the wrong answer. First, the most frequent mistake I see is students applying surface area logic to volume. Remember what we discussed in slide 2? When we joined shapes together, some faces disappeared from the outside, so we had to subtract those areas. However, as we learned in the previous slides, volume is different. The space inside doesn't disappear just because two shapes are touching. So please, do not try to subtract the joining area from your volume calculation. For volume, you simply add the parts together. Second, be very careful with the incorrect identification of parts. You must be meticulous when decomposing a complex object. Let's look back at our medicine capsule example from slide 4. If you accidentally forget that there are two hemispheres and only calculate for one, your entire final result will be incorrect. Always double-check that every component of the object is accounted for in your sum. Finally, always watch out for mixing units. This is a classic trap in mathematics. Before you start plugging numbers into your formulas, ensure that your radius, height, and length are all in the same unit, for example, all in centimeters or all in meters. If you add a volume in cubic centimeters to a volume in cubic meters, your answer will be meaningless. If you can avoid these 3 mistakes, you will be well on your way to mastering the principle of additive volume. Let's move on to our final summary. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways so you can approach any complex shape with confidence. First, remember the additive nature of volume. As we discussed throughout this session, volume is additive. This means that when you are dealing with a complex object, the total volume is simply the sum of the volumes of its individual parts. You don't need to worry about any complicated subtractions here. Second, keep in mind the independence from joining faces. This is a crucial distinction we made earlier when comparing volume to surface area. Unlike surface area, where the faces that touch each other disappear from the outside, the volume of a combined solid is not affected by the fact that some faces are hidden or joined together. The space occupied by the material remains constant, whether the parts are separate or glued together. Finally, I want you to memorize this general approach for solving these types of problems. Whenever you encounter a new, complex shape, follow these 3 steps. 1. Break the object down into basic, recognizable geometric solids, like the cylinder and sphere we saw in our medicine capsule example. 2. Calculate the volume of each of those basic solids using your standard formulas. And 3. Add those individual volumes together to arrive at your final result. If you follow this systematic method, you'll find that even the most intimidating shapes become much easier to manage. Great job today!